This satellite foundational course for GOES-R will teach you what you need to know about the scanning of the Advanced Baseline Imager, the ABI, on GOES-R. In addition, you'll learn about the improvements on ABI related to spatial, spectral, and temporal resolution, how parallax can affect what you see, and how multiple satellites with different resolutions will view North America. The authors of and contributors to this training are listed, and they all work, or worked, at the University of Wisconsin-Madison Cooperative Institute for Meteorological Satellite Studies, SIMS. Learning objectives for this module are listed on the screen. Take some time to read through them. Some of the radiation knowledge you will have learned about, or will see again, in other modules. This slide was from Jordan Girth, Noah Nestis. There was an immense increase in the amount of data sent by the ABI compared to previous GOES imagers. The ABI on GOES-R acquires a full disk image up to 5 times faster than the previous imager on GOES 13 through GOES 15. Spatial resolution on the ABI increased by a factor of 2 in both horizontal directions. And there are about 3 times more spectral bands on GOES-R. The cubes represent the data volumes from legacy GOES in dark orange-red, and the new GOES in yellow-beige. The combination of increased resolutions meant at least a 60-fold increase in the data volume. These increases did cause issues, mostly resolved, in storage and retention of the data. This is the ABI scanning strategy as of April 2019. This is mode 6. The blue regions are where CONUS scanning was happening. They take about 2.5 minutes of wall time. Green regions are mesosector scanning. The time of the image is always the start time when the first pixel, usually the upper left as you're looking at it, is scanned. These time charts show when and where the ABI is scanning in strips of 30-second intervals across the top. So there are sequential 30-second strips that start on the left-hand side. During the 10 minutes shown on this chart, 1 full disk image is scanned, 2 CONUS images are scanned, and a mesosector is scanned 20 times. Alternatively, 2 different mesosectors can be scanned 10 times. White space on this chart is instrument idle time. No radiation is being sensed. This is the time chart of continuous full disk mode. Note the relative lack of white space. This is the highest data rate for GOES-R's ABI and results in a full disk every 5 minutes. No mesos are being scanned when this is happening. This kind of scanning mode might be used if multiple high-impact weather and/or volcanic events are happening within the GOES-R footprint, or if GOES East or GOES West are non-functional. The initial default scan mode for GOES-R before April 2019 was mode 3, or flex mode, shown here. You see 1 full disk image every 15 minutes, 3 CONUS scans in those 15 minutes, and 2 mesos being scanned every minute. This scanning strategy had a lot of idle time, and that idle time was repurposed when mode 3 was replaced by mode 6 in early 2019. If you're looking at historical data from before April 2019, this is the mode you have to remember. The default scanning now for mode 6, just to repeat, 1 full disk image every 10 minutes, 1 CONUS, or for the GOES West, I might call that PACUS, image every 5 minutes, and 2 mesoscale sectors every minute. You can also overlay mesoscale images to get 30-second scanning. You can find at the link shown the priority list for mesoscale sectors. If you fall within a default mesosector and your weather awareness will benefit from satellite imagery at 1-minute intervals, make sure you call a meso. Otherwise, someone else might make a request that repositions the scanning someplace else. This figure shows spatial resolution, pixel areas are approximate, as a function of color for GOES-R and the GOES-West position. The PACUS, which is the GOES-West version of CONUS scanning, and default mesosectors are shown. Mesosectors are movable and are 1,000 by 1,000 kilometers in size at the subsatellite point. They always have the same number of horizontal lines and vertical elements. For bands 1, 3, and 5 on ABI, a spatial resolution of 1 square kilometer occurs at nadir, the subsatellite point. Each color bin in this image is rounded to the nearest square kilometer. The first dark blue ring labeled 1 shows pixel areas from 1 to 1.5 square kilometer. The next lighter blue shows pixel sizes between 1.5 and 2 kilometers squared, labeled 2, and so on. For band 2 with native half-kilometer resolution and all other bands with native 2-kilometer resolution, you should multiply the approximate pixel area by 0.5 or 2, respectively. A special note here, prior to March 2019, the GOES-West mesoscale sector to default was over the central United States. In early 2019, it was repositioned to be over Alaska. This is the same figure for GOES-R in the central GOES test location with the CONUS sector indicated and 2 mesoscale image sectors shown. All GOES-R satellites start at this point for 6 months of testing or more before they are moved to the east or west location. Here is the figure for GOES-R in the GOES East location with the CONUS sector indicated. The default location of the mesosectors is shown. Remember, they can be moved anywhere. This is for GOES 16 before April 2025, or GOES 19 after April 2025. If you're in a WFO and you want satellite imagery more than every 5 minutes over CONUS or PACUS, or more than every 10 minutes, call a meso. This website tells you current and future planned mesos. If the default is over you might want to call a meso anyway just to make sure it stays there. There is also a list of priorities to mesos that you can see if you click the color legend button. Calling a meso varies by office and region. It usually involves a Google form that is filled out and pushed up the line through regional to the senior duty meteorologist who contacts the satellite operations. The reasons for the mesoscale sectors shown at this site are shown. Bookmark this site. This table shows the better spectral, spatial, and temporal resolution of the ABI. What does on-orbit calibration mean for the reflective bands? That means GOES East visible and GOES West visible will look similar even as the satellites age. This table is based on a 2017 paper by Schmidt et al. There are 16 bands, the central wavelength, the wavelength range, the resolution, and the band nickname. If you're in Pacific region and using AHI data from Himawari 8 or 9, there are some differences. AHI has a green band, 0.51 micrometers, and doesn't have the Cirrus band at 1.37 micrometers. The central wavelengths are sometimes slightly different, but not in a substantive way. The reflective bands shown here have little utility at night. An exception might be the 1.6 and 2.2 micrometer channels that can have a signal for fires and volcanoes. Band 2 on ABI continues observations at 0.64 micrometers that were done on previous GOES imagers. That's what that star means, that the band was on a previous GOES satellite. Note that bands 1, 3, and 5, the odd numbers, are the bands with 1 kilometer resolution. Band 2 has half-kilometer resolution, that's the best, and bands 4 and 6 have 2-kilometer resolution. These are the infrared bands on ABI. The number of IR bands increased by a factor of 2.5 from previous GOES imagers. As on the previous slide, you have the band, the central wavelength, the wavelength range, the subpoint pixel spacing, 2 kilometers for all of these, and a descriptive name. Stars appear approximately where GOES imagers observed data in the past. Bands 7 and 16 have close matches on legacy GOES imagers. The water vapor channel and water vapor bands on ABI are similar, but not exact matches to legacy GOES. NOAA desires observational continuity across GOES platforms, but channels are added and resolution increases with sequential GOES programs. That'll continue with the next geostationary satellite program, GeoXO. Here's a graphical image of all the GOES-R bands centered at 89.5 west, the test position. A lot more data flows from GOES-R. The same enhancement is applied here to all the infrared channels, and you see that the window channels, 7, 11, 13, 14, and 15, show warmer or redder temperatures than channels where absorption by various gases occur, either water vapor in bands 8, 9, and 10, ozone band 12, or carbon dioxide band 16. This shows the spectral response functions for the visible and near-infrared bands, as well as reflectance for different surfaces. These ABI bands, as mentioned, are useful mostly only during the day, with some exceptions for the 1.6 and 2.2 micrometer channels. Surface reflectivity differences between bands means that what is evident in one band might not be quite so evident in another. For example, snow is bright white in the visible. Reflectance is quite large. But it's not very reflective at all at 1.6 micrometers. There's a lot more absorption. This is handy when using the 1.6 micrometer band to monitor glaciation in a cloud. Some sample uses for the bands are listed, but many more exist. The blue regions in the spectral response function show where energy is being detected by the satellite. So in band 5, it's not just looking at 1.6 micrometer data, it's looking at data in the range between 1.59 and 1.63 micrometers, approximately. The red line in this figure shows brightness temperatures that would be computed from satellite observations at various wavelengths above a U.S. standard atmosphere, assuming a clear sky. The spectral response functions, that is, where infrared energy is being detected for the infrared bands on ABI, are shown in blue, as well as the band number and the band nicknames. In some regions, around 10.3 micrometers, for example, atmospheric absorption is small, and the computed brightness temperature is the surface temperature of the U.S. standard atmosphere. The satellite at that wavelength is detecting radiation emitted from the surface that escapes directly to space. In contrast, energy at 6.5 micrometers or at other wavelengths that leaves the surface is absorbed strongly by water vapor in the atmosphere and then re-emitted from a higher, colder region. At some point in the vertical, when water vapor no longer exists above a region, the re-emitted energy will escape unabsorbed to space, but it will be from a far colder region, so a colder temperature is shown. In addition to water vapor absorption, absorption by CO2, SO2, and ozone is also present. The different bands or channels had different uses, as shown here. There are lots of other uses too. Let's switch topics now. Parallax is a well-known misnavigation that happens when something, a cloud feature in the atmosphere, blocks the satellite's view of the surface. The characteristics of parallax are shown on this slide. In clear conditions, satellite observations come from the surface pixel, and that information is navigated to that point. All satellite navigation assumes clear skies. If a sensor is pointing in a particular direction, the navigation places that information at the surface. A cloud that develops between the pixel and the satellite, however, will mean that information from the surface is blocked, Instead, radiation will come from a region that is closer to the satellite, but that is nevertheless navigated to where the straight line emission from the Earth would have originated in a cloud-free atmosphere. The satellite sensor is still pointing in that same particular direction associated with the surface point. The misnavigated point is always farther away from the satellite subpoint. Parallax error is related to how high a cloud is and how far that cloud is from the subsatellite point. As clouds get higher and higher, the parallax shift gets larger and larger. As clouds get farther and farther from the satellite subpoint, the parallax shift gets larger and larger. Note that satellite observations in AWIPS typically are not parallax corrected. This linked to website shows how information would have to be shifted to get to its actual correct geographic location. In other words, how do you remove that parallax shift? The information is observed and navigated by the satellite to be too far from the subsatellite point, and the shift to the correct location is always toward the subsatellite point as shown here. This particular example is for GOES West and for clouds that are 50,000 feet high. Here's an example comparing GOES-R infrared data from the test position at 89.5 west with MRMS radar. Note that the echo cores are offset from where the coldest cloud tops exist. Those yellow circles are in the exact same location on either image. Remember parallax shift if you're on the satellite during an event when radar is also being used. You should be able to accustom yourself to typical parallax shifts in your WFO. It's not going to vary much across the CWA, but if you're in OPC, WPC, or at HFO and doing marine forecasting over a large area, parallax changes can be large across your area of interest. Similarly, if you're doing mesoanalysis for a different office during a severe weather outbreak helping them out, the parallax shift there might be different from what you're used to. The importance of 1-minute sampling is pretty well known. GOES-R offers mesoscale sectors with 1-minute sampling so that better monitoring of cloud top features, or fires, for example, are possible. Examples are listed at the URLs. In addition, the figure insert shows brightness temperatures for the Buffalo, Oklahoma fire of February 18, 2016 at 1-minute increments. The red dots show how the fast-changing fire would be sampled at 5-minute increments. Many quick changes are missed with only 5-minute sampling frequency. So if you're in a red flag warning or if you're monitoring fires, make sure you have a meso called for your WFO. An important part of mesoscale sectors on GOES-R is that they are movable. If something, the figure shows Tropical Storm Aletta in the Pacific Ocean, occurs outside of routine CONUS 5-minute scanning, put a meso on top of it to see what's happening with better temporal resolution than with the full disk 10-minute scanning. Which GOES-R satellite should you use, and which GLM instrument should you use? Let's talk a little bit about that for GOES-R. GOES East and GOES West have resolutions that degrade as you move from the subsatellite point. If you're in the Rockies or High Plains, choose wisely. The resolution is about the same at 106 degrees west. So to the west of that, GOES West has the optimal resolution. To the east, you'd probably want to use GOES East data. Congratulations to WFO Glasgow that has the poorest resolution over CONUS for scanning. If you combine GOES East and GOES West CONUS and PACUS scans, you'll notice you get a very large geographic region with 5-minute scanning. Acronyms that you saw in this module are listed here. You can find a list of links mentioned throughout this training on the launching page. This is a summary to remind you of what you have learned. This is the conclusion of the Satellite Foundational course for GOES-R on basic operations of the ABI on GOES-R. Thank you for your attention.